Okay, so I'm going to talk about a trick to evaluate impossible double integrals. So to evaluate an impossible double integral, something that looks like this. Let's say 0 to 1, x to 1, sine of y squared dy dx. The problem is to evaluate this thing. So first of all, remember the rule. You will never see in this class an impossible integral. There's always a trick to doing it. So the problem, it's always just to find a trick. There's no typo, or it's not impossible. It's just that you have to spot where is the simplicity. So the simplicity of this integrand, it only depends on y. And that's really what saves you. Right? If this had just this had an x in here also, then I think that would be a huge problem. But fortunately for us, this is actually a doable integral. First of all, let me just recall, why is this kind of an impossible integral? Why did I call it that? It's because sine of y squared dy, that cannot be evaluated. So this is impossible. This 1D integral. It's an impossible 1D integral. If you are interested, it's called a Fresnel integral. It arises from optics. But what's actually good about this is that there's it's in the context of a double integral, and the double integral has some nice properties. So I would say it's a good double integrand. So there's only a y there. That's really what's going on here. And what that extra integral does for you, so the extra x integral, to summarize, it will add a y, adds an extra y after the first iteration. I mean dx. After you apply the dx, that will add an extra y. So now you have y sine of y squared, and now you can use u substitution. And that's routine. Okay, so the question is, how do we get that extra x? How do we get the extra y? How to get the extra y? Well, really, it's Fubini's theorem, right? Because we want to do the x integral first. But it's not a rectangle. So that means we need to change the limits. So the limits will shift. Right? Because if I did a rectangle 0 to 1, 1 to 2, or let's just say a to b, then the limits would stay the same after exchanging if it was a rectangle. Right? But now, what is our region? Our region is, it depends on x now. Right? Because it was the integral from x to 1, and this is the y integral. Okay, so how do we do this? So I'm just rewriting it. So there are a couple steps to do. So the first one is we're going to draw the original region. Okay. So if we draw the region, we need to know first what the region is. So I'm going to, yeah, remember x is on the outside. So x ranges from 0 to 1. And y is on the inside. So now I'm going to write the y limits, and that's what we have for that. It ranges from x to 1. So what we do now is we draw the region, we draw the x's first. X is 0 to 1. That's okay. So now we draw the y second. And we'll have an x, and then we'll have a 1. So x, that's just this line. Okay? And so y can be anything in between here and here. So really, your y can be, your y constrains you to be this region. Okay? So now that we have the region, we're going to now reverse the arrows. Reverse the integration arrows. Okay, so I'm just going to redraw the region just to make things clear. So here's y, here's x, and here's our triangle. So now I'm going to change that up arrow to a side arrow, and I'm going to change this side arrow to an up arrow. This is still 1, this is still 1, and this is still x. But now, the line y equals x, I want it to be x as a function of y. Right? Because now if we started with this type 1 region, now really what I'm wanting to do is a type 2 region. So y is the upper limit and in the x integral, and then 0 to 1 will just be our y limits. So our x's, if we start from the inside, our x's are going to go from 0, that's this is x equals 0, and it will end with y. And our y's will start with 0, and they'll end with 1. So this allows you, so this is the inside, and this is the outside. So now, we can fill in this information to our integral. So now write the integral. Inside to outside. First, let's do the inside. The inside is our x. So the x goes from 0 to y. Now let's do the outside. The outside is y. So we put a y here on the d, and then we put a 0 and a 1. And then, of course, we need our function. Our function is the same. That's sine of y squared. Okay, so the integral from 0 to 1, 0 to y, sine of y squared dx dy, that's our integral. Okay, now this is so much better. This is so much better, right? Because we're doing, if we start with our x integral, we can actually take this stupid sine of y squared, we can take it out. So we end up with something really easy. the integral from 0 to y of dx, that gives you y. There's our extra y. Okay, so we're left with the integral from 0 to 1 of y sine of y squared dy. And that is a very doable integral. Okay, so the upshot is if you see an impossible integral, try exchanging the order of integration. To get an extra y. Let's just say an extra prefactor from your integral. And we want the prefactor to hopefully be helpful. Okay, that's all for this video.